So now let's do the proper introduction. So welcome to the Northwest Database Society talk series. We're super happy to have with us today Professor Juliana Freire. Juliana is well known in the database community. She's one of our senior and very prominent members. She's a professor of computer science right now and data science at NYU. She was the elected chair of the ACM SIGMOD, served as council member for the Computing Research Association's CCC, and was the NYU lead investigator for the Morse Sloan data science environment, which was this huge initiative. And actually, the UW, we were also part of this really large grant. So Juliana does a lot of really cool work, especially around, all kinds of, so I'm getting some notifications here, but that's okay. So her work spans kind of a large breadth of work in the database community, including data visualization, machine learning, provenance management, web information discovery, different application areas, including urban analytics, predictive modeling, and computational reproducibility. Juliana has so many awards, I can't even read all of them, but she's an ACM fellow, a AAA fellow, and that should give you a kind of sense of how prominent Juliana is. And we just feel so fortunate. Thank you for making the time to be with us today, and then we look really forward to your talk.
Okay, thank you so much, Magda, for the kind introduction and for the invitation. So today I'm going to talk about a relatively new project that we have here at NYU on trying to address this big problem of data set search and discovery with applications to data augmentation and explanation. And I'll get to that in more detail shortly. Right, so this is joint work with a number of people here at the Visualization, Image, and Data Analysis Center, students, postdocs, and colleagues also. So why is this a problem? So we live in a data-rich world. Our increasing ability to collect, catalog immense amounts of data about our environment, society, people, right, together with the push towards transparency and openness, has led to an explosion of open data repositories. And that's for government data, city data, urban data, and you name it. So there's tons and tons of repositories with these open data sets. This is also true of the scientific world. We have seen a similar trend through the open science movement. We have many data sets in different domains, from biology, physics, geosciences. And recently, the White House, OSTP, actually released a memorandum that actually, is trying to institute new policies to ensure that the free, immediate, and equitable access to federally funded research. What means is that, NSF and NIH and all the federal agencies now are going to mandate that whatever research you do, that you use federal funds for, you have to publish your papers, but you also have to publish all the data supporting the results in your paper. So we are likely to see a much bigger increase in the number of open science data sets, right? Just to give you a point of, in terms of like the number of data sets that are out there. In a paper in ISWC in 2020, Omar and Natasha published some statistics about Google dataset search. And at that point in time, they were indexing 28 million data sets from more than 3,700 sites. Natasha was here last week, and this number has grown already to 43 million. And that's just the data sets that they index. They estimate that there are between 200 and 300 million open data sets on the web, right? And it goes without saying that, in industry, there's also been an explosion in data sets that are available, not just in databases and warehouses, but now in these, data lakes and cloud storage. And these are great news, because with all these data, we have lots of opportunities to enrich analytics, to be able to derive data-driven explanations for features that we find in data, as well as to create and improve machine learning models through data augmentations, right? So here I have a few examples of what we can do if we can discover data, right? So this blue these blue bars here show the number of traffic deaths by year in New York City, right? You can see, some trends. It went down, and then, around 2013, it went up again, and then it went down. So, what could explain these trends? We know that in 2013, it was when the city bike actually started in New York City. So you may ask, is it the case that the increase in the number of bikes, active bikes in the city, actually increased the number in fatalities? Right. If data is out there, you can discover data and try to use this data to explain, or to prove or disprove your hypothesis. Right. And then in 2014, as part of the Vision Zero initiative, there was a decrease in the speed limit in New York City. And as we can see here, there was a decrease in the number of fatalities, right? Is it the case that it was the reduced speed limit that actually reduced the number of fatalities? Right. And again, we can discover and use data to try and, study or prove or disprove this hypothesis. In terms of machine learning models, one model that is, very much used here in New York City is one to predict taxi demand. And people usually use historic taxi trip data in order to predict future demand. However, there are many other factors that may affect the taxi demand, like, for example, events that happen in the city or, bad weather. Right. So is it the case that we can actually improve taxi demand prediction if we augment the historical trip data with data about weather and major events? Right. So, and there are many other instances where, if you discover data can actually enrich your analytics. And here's a short video of a tool that we developed here at NYU that helps architects explore and compare different neighborhoods in New York City based on different indicators like access to taxis, subway, noise, crime, and so on and so forth, right? So, if you can find data, you can do lots of, useful, you can obtain useful insights from this data. Right? And that's great. The more data we have, the better, right? Maybe, because you can have lots of data available, but it may be difficult to find data that is relevant for your particular task or information need. And nowadays, data discovery is a major bottleneck in data-driven exploration. There are estimates that say that data scientists spend a substantial amount of their time just trying to find data for their analysis, right? And one of the challenges comes from the fact that these data sets are spread over a number of different sites and repositories, right? And search engines have solved this problem for documents, right? And we are seeing a number of approaches out there that are trying to do the same thing for data sets. So the idea of these data set repositories and data set search engines is to organize data sets or just their metadata in centralized repositories to make it easy to actually search for these data sets. And here there are three examples. One is NYC Open Data, which is a vertical that puts together all data sets that are released by New York City agencies. Here is the Harvard Dataverse that actually publishes data that are submitted along with papers in social sciences. And on the right here, we have Google Dataset Search, which actually piggybacks on the Google crawler to discover data sets that are published on the web. Right? I don't know, are you guys familiar with Google Dataset Search? Yeah, so it's actually an interesting idea. It actually relies on the data publisher to publish a schema.org record, right? So when the Google crawler sees a schema.org record that defines a data set, that's ingested and then indexed and searchable through this particular interface, right? So the way that these data sets or these repositories this work is, very much like your traditional search engine. You can enter a keyword, like, for example, city bike, and these systems will return a list of snippets, textual snippets, with some description of the data sets. However, even though this works well for web documents, I argue that this is not ideal when you're actually dealing with data sets. First and foremost, it's very difficult to express information needs or specify what you need in a data set using just keywords. And it's also very hard to assess whether a data set is relevant based just on these textual snippets. On top of that, the search and the snippets are produced based on metadata that is published together with the data set by the dataset owner or publisher. And this metadata is necessarily incomplete. And in many cases, I've seen, in particular for open data, that it can actually be inconsistent with the data. So I've seen data sets that say, taxi data for 2016, but it actually contains records from 2016 to today. Right. There's a number of people that have started to look at this problem. And in a recent study, Pappenmeyer and colleagues, they actually did a big survey with social science researchers. And they found that there is a huge mismatch between the user requirements and the metadata and search capabilities that are currently provided by these repositories. Right. And in the end, these repositories may be useful if you know what you're searching for, but they have very limited, and it can be very hard for discovering what you don't know, right? The unknown unknowns, as Don Rumsfeld, nicely put a while back. So what we'd really like in terms of, data discovery is that, what we really need to do is to go beyond the metadata that is provided by the data publishers. And we should leverage the data set contents as well as relationships between different data sets. And I'll explain this in more detail shortly. We also need better mechanisms for searching these dataset collections. We need more expressive queries that are able to capture a wide range of information needs for different analytic tasks. And last but not least, we need informative snippets and the better ways to actually interact with the search results so that it's easier for users to identify what data is relevant and can answer their question. So looking at the data, we started to work on a system, dataset search engine, which we call Auctus, that tries to rethink this problem of search with data sets in mind. So we use the basic structure of the architecture of search engines to try and figure out how to address the unique requirements for data set search. Right. So the first one is how do you actually populate your search engine, right? So first you have to discover data sets. And unlike crawling the web, where you're crawling web pages that have links and link to each other, and you can do this recursively, the same is not true for data sets. You don't have links between the different data sets. So we actually need new mechanisms to search the web and discover repositories and individual data sets. And we have done some preliminary work on this. In fact, we built a focus crawler that tries to find data sets for particular domains. The second component is, is not present in traditional search engines, which is, this profiling, right? So instead of relying on the description provided by dataset publishers, we developed a collection of profilers that automatically derive metadata from the actual data, right? And, shortly you're going to see what I mean by that. And we use these metadata not only to support keyword search queries, but also other types of queries that cater to different information needs. And finally, we've also been exploring methods to generate better summaries, more informative snippets that are better suited for data sets, right? So what I'll do next is I'll show you a video that kind of like provides a short demo of some of the features of Auctus. And let me see if I can play this. And there's sound. If you cannot hear, let me know.
Okay, so we don't hear anything, we just see.
You cannot hear it?
Oh.
Oh.
So when you did the share your screen, I don't know if you clicked share with sound.
Let me see if I don't remember seeing the option. Let me try to do it again.
Yeah,
oh yes, here. Good.
Is a search engine like Google, but for datasets.
Okay.
Yep.
Similar to Google, you can pose keyword-based search queries. For example, you can search for datasets on cyclist behavior by typing in the search box. Auctus then retrieves and ranks the most relevant datasets from its index. For this particular example, Auctus fetched over 30 results. We can quickly inspect them. Let's explore the highest ranked result, cyclist crashes in Australia. Its snippet on the left shows key features including its description, the names of its columns, and their data types. Before adding a dataset to its index, Auctus profiles its contents to derive metadata. Here, you can see that the profiler detected both temporal and spatial attributes. When you click on a result snippet, you can see a summary of its contents. For example, the user can inspect the spatial coverage of the dataset on a map. Users can also inspect a sample of the dataset contents, the columns with the inferred data types, and by selecting column view, they can see statistics for the columns. The goal is to provide enough details about each dataset so that the user can more quickly ascertain its relevance. If the user finds the dataset relevant, she can then download it. A novel aspect of Auctus is that it supports a rich set of data discovery queries. Besides keywords, users can also explore dataset collections based on space, time, and data relationships. For example, if the user is interested in datasets about bicycle usage but only in the United States, she can type cyclist in the search box and additionally click on any location to specify a spatial constraint. Here, she can create a polygon around the US. Note that the results now only show datasets from the United States. We can also specify a time period of interest to find datasets that are more aligned with our information needs. If we want the most recent data, we can search for datasets from 2019 to 2021. And we can also specify the desired temporal resolution, for example, with timestamps on a daily basis. Auctus allows data augmentation queries. Let's suppose that an expert in the New York City Department of Transportation is trying to understand bike usage in New York City. She searches for relevant datasets by typing a simple query in the search box, and after some inspection, she decides to use a dataset on bicycle trip counts on the East River bridges. She wants to use it to create a model to see if daily temperatures, represented by attribute height temp, help predict the number of bikes crossing the bridges, represented as total. Unfortunately, this dataset only covers the month of April 2020, which is not enough to understand how bicycle usage varies throughout the seasons. She then goes back to the snippet of the dataset and presses button Search Related to see if she can find more compatible data records to build a model. She sets the option Augmentation type as Union and then re-executes the search. By inspecting the resulting dataset, she sees that it contains the same kind of data, but stemming from May to October 2020. The Augment Options tab informs her that a union can be performed between her input dataset and this new dataset, listing the matched attributes. By pressing the Merge, Union, and Download button, Auctus automatically performs the union and downloads the augmented dataset to her machine. She then creates a simple regression model to see if daily temperatures are good enough to predict the number of bicycles crossing the bridges. As we can see, she obtains an R-squared score that is close to 0.25. This model is probably underfitting the data for lack of features, as it relies only on temperature to make predictions. Using Auctus, she can search for additional features for her model. By uploading this augmented dataset, she can search, for example, for weather-related datasets that are joinable on datetime to include more features on a daily resolution. After inspecting the results, she selects the augmentation with dataset Weather Data NYC 2020, which includes information about rainfall. She then selects the attributes she wants to keep and downloads an augmented dataset. When rerunning the random regressor over this new dataset, the R-squared score increases to approximately 0.56, a significant improvement. Auctus allows users to filter results by data type or source. We also provide a Python API and an HTTP API to access the search engine. For more information about Auctus, check our GitLab or GitHub repositories.
Okay.
Auctus is a search engine.
Sorry. All right. So I guess it gives you like an idea.
Auctus is a search
Sorry. Let me see.
engine, like Google.
It doesn't want to leave. Okay. Finally. All right. So that is the, kind of like the basic idea, and the main motivation to actually build the system came from this DARPA project called D3M that had as the objective to develop automated model discovery systems, essentially, build end-to-end, synthesize end-to-end machine learning pipelines, right? And one thing that we realize is that there's so much that you can do with machine learning algorithms, but there's a lot that you can do by having better data, having more data. Right, so that's what's kind of like the main motivation for this project, and one of the examples that we used was similar to what we had in the video, which is you have a data set. In this case here in the slide, we want to predict taxi demand. We have pickup time of the taxi trip. A time, a location, and the number of trips that happened at that time and location, right? And the idea is that can we actually create a model that predicts taxi demand? And when we use, say, a random forest regression, you get an error that is quite high. And the question is, can we find data sets that have additional features, right? And yes, there's lots of data out there, and if you're an expert, you know that weather affects taxi demand. So you can use something like Google dataset search and look for NYC weather, and you're going to find relevant data sets. Once you find the data sets, you need to do the join, retrain your model, and boom, you have your improvement, right? So this is great. However, this actually requires you to know beforehand what you're looking for, right? So another way that you could improve this model is maybe looking at the information about city bike, right? So you can search for city bikes, and you're going to find some useful data sets, but you may find too many of them. So if you see here in the search, there are 1,006 results. Right? And the question is, do these actually overlap with your training data? And are they going to improve your model? Right? Using Auctus, you can do a little better, and you can search just for data sets that overlap. So the first question is answered. But if you do that right now, for that particular data set, you find about 3,964 results, which is too many to go through. Right? So the question is, which ones, amongst these will actually lead to improvements in your model? A good thing about this problem that makes it tractable is that, when you're trying to do relational data augmentation, you can automatically check whether, these candidate data sets actually improve your model or not. So if you have a data lake with lots of candidate tables, you have your query table, your taxi trips. There are actually techniques that can efficiently identify the data sets that are joinable with your query data set. right? So you can go ahead and you can, join them and train your model and check if the performance is improved or not. And although this can be automated, when you have very large collections, this is really not feasible to do. Right? It's just too expensive. And then the question that we ask ourselves is, can we efficiently find variables in these large data set collections that can help predict a given target variable? Right. So this is the first question that we try to answer. And to answer this question, we propose a new type of query, which we call joint correlation queries, which provide a data-driven approach for data discovery. And the idea is that given a query table, we'd like to output tables that are both joinable and have columns that are correlated with the query data. So going back to the taxi demand model, we'd like to find all data sets that are joinable with the historic taxi data, but that also contain an attribute that is correlated with the target variable number of trips, right? So the intuition here, and one of the reasons why these queries can be very useful, is that correlation is the basis for a number of, analytic tasks, right? And the intuition you can see by looking at linear regression, which is widely used to estimate parameters in a linear equation that predict the values of X and Y, right? So in a linear regression, you're estimating the parameters B0 and B1 in this linear equation using data from Y and X. And if you think about Pearson's correlation coefficient, it can actually be seen as the standardized slope of this regression line, right? So it's B1 equals R Sx over Sy, where these are the standard deviations of X and Y, right? So this means that the stronger the correlation is, the higher the predictive power of a given variable is. So the idea is that by finding correlated data in large table collections may help us explain or predict other variables of interest, right? So the problem that we try to solve more formally is what we call top K joint correlation query, which given a table that has a key column, a joint column, and a target column Q, you'd like to find the top K candidate tables such that the table is TC is joinable with TQ on the key. And the table TC contains a column that has the strongest correlation with the variable Q, right? And what is, and the challenge here is that we'd like to get this correlation information between X and Y after you actually perform the join. If you have two tables, the X and Y, right, you have to join them in order to be able to compute the correlation between the X and Y values that are aligned after the join, right? And, there has been work that looked at variations of this problem, simplifying correlated columns in a single table, right? And that where the table is already aligned, so you have aligned vectors. And there's also been work on finding tables that are joinable, right? And for that, people have proposed strategies that, try to compute the actual exact overlap between the tables. And there's also approaches that, try to estimate this overlap or the join size, right? So in our case, we propose an approximate solution for this joint correlation estimation that trades off accuracy for performance. And our approach works in two steps. First, we discovered the top K most joinable tables, the tables that have the highest overlap. And in the second step, we actually re-rank these candidate tables using correlation estimates, right? So this is, more or less what it would look like. We have a data lake with a set of tables. For each table in the data lake, we generate a sketch of size n that is much smaller than the original the size of the original tables. We index these sketches, and we can use here an inverted index. And then when a query table arrives, we generate a sketch for that query table, and we try to find the matches in that index and return the results with the estimates for the correlations for each of the candidate tables. All right.
I have a question.
Sure.
So one question, just to make sure I understand correctly, when you look for joinable tables, do you always join on some kind of unique identifier of the main object? Because like in the example of the New York City taxi trips, I'm interested in how long the taxi trips take. So then I can find another data set that I can join on some identifier of taxi trips. But I could also join, for example, a data set that maybe just joins on location and has information for that location. So that will be joining on another attribute. So can you talk more about how do you decide if two tables are joinable and which attributes used for the joining?
Right. So right now the approach relies on joins on the keys are categorical attributes, right? And for space, you can actually there are actually strategies that can transform lat long or a location into strings that could also be encoded here. So we can support space, but then you have to hash into a string that would actually be supported by this approach. Does that answer your question, Magda?
That does make sense. So then it has to be a categorical attribute, but it doesn't have to be like the primary key of the table. It could
no, it does not. Yeah.
Same table, just as long as it's categorical, then you do it. Okay, thank you.
Yeah. Okay, no problem. All right. So the basic idea here is to use these sketches to estimate overlap and correlation, right? And as I said, the challenge is you have to estimate the post-join correlation without computing the join, right? And here, what is difficult is that, if you random sample the column vectors, you're not going to get good correlation estimates. And similarly, if you just sample rows randomly, it's not going to work because the values need to be aligned using the join key so that we can produce the, good correlation estimates, right? So we propose this idea of correlation sketches, which is an extension of KMV, right? And the basic idea is to use hash functions to create a data sketch for each table. And by doing so, we're able to recover a uniform random sample of the resulting join without having to compute the full join. And because we can do that, we can actually apply any correlation estimator over the sketch join, Pearson, Spearman, and so on. Right, and with using these correlation sketches, as I illustrated 2 slides ago, you can build an index of these sketches to support fast table retrieval, and we can perform, because the sketches are small, we can do this fast correlation estimation at query time. Right. So how does how do we construct these sketches? Again, it's very similar to KMV. So the idea is that given a table. And let me see, right? We first hash each key. We create a hash of each key in that particular table. Then we map the hash into the unit interval, and we keep the K values, the smallest values in that particular interval, right? And, we associate that with the value that, the numerical value that is part of the sketch, right? So in essence, we don't need to store this unit value. We only need to store in the index the hash value and the numerical value, right? And to find joinable tables, all that we need to do is to do the set overlap search. We find tables that have the highest overlap of the hash join keys, and this is something that can be done really efficiently using inverted indexes. Once we find those tables, to estimate the correlation, it's again very simple. These are tiny sketches. We can do these joins in memory very efficiently. And then we can apply the, any correlation estimate that you'd like. So as I said, you can estimate, not different correlation measures, but you can also estimate join size, Jacquard containment, Jacquard similarity. Right? So the question is, does this work in practice? So we ran a number of experiments using both synthetic data and real data. So for synthetic data that, follow by their normal distribution, the results are great. So in the x-axis here, we have the actual value for the Pearson's correlation. And on the y-axis, we have our estimates. And you can see that the errors are very small. And the estimates, are right along the diagonal, right? When we look at real data, and we got data from World Bank and NYC Open Data, then we have much higher variance in terms of the estimates, right? For many points where the actual correlation is 0, right here, right? You have, both overestimates and underestimates, right? Because in these large collections, most of the data is actually not going to be meaningful, right? It's not going to be, good correlations. Having these errors will mean that we can end up with lots of false positives when we present the results back to the user. So we looked into this with more detail, right? And one of the things that we noticed is that, yes, the estimates can be pretty bad, but the size of the joins for the sketches, the resulting joins of the sketches, in many of the cases is very small, right? And not meaningful. When we filter the sketch joins and we only keep joins with size 20 or more, then we see a much better behavior where the estimates are actually, much closer to the diagonal, just like for the synthetic data, right? We further investigated this problem, and one thing that we realized is that we can compute confidence interval bounds for the estimates that we give, and we can use this to detect when the estimates are not good, right? And what we did was to use these bounds to actually rank the result set, right? So the idea is that we want to avoid placing uncorrelated columns in the top of the ranking. And for that, we developed this very simple scoring framework that, instead of just using the correlation coefficient, it will dampen that by the risk that estimate is actually not good. And this risk can be computed using different statistical methods like Fisher-Z transformation. And the drawback there is that it assumes that you have a normal distribution. You can also use bootstrapping methods, but these are very expensive. And what we proposed was actually a new method based on Hopkins-based encoding. And we showed that, using that, we can efficiently compute those bounds, and the ranking that results is actually very good, and put the really highly correlated tables on top of the ranking. Okay. Okay. So the other question is, is this efficient? Can we actually get, interactive response times when we use these sketches? And the answer is yes. So in this table, what I'm showing is the average time for computing the joins and correlation measures, Spearman, Pearson, over the full data versus using the sketch, right? And as we can see here, using the sketch, we can actually compute the estimate the correlation in 3 orders of magnitude faster than just computing the full join. Okay. We also experimented with the end-to-end process, not just the correlation estimation using the sketches, but also hitting the index, retrieving all the tables and ranking them and so on. right? In these experiments, we observed that 98 of the queries run in less than 200 milliseconds, and for the 94th percentile, it's actually less than 100 milliseconds. So these results show that the approach can indeed provide interactive response times for dataset search over large collections. Right. So the benefits of this approach are clear. We can do these estimates, which are good estimates without having to perform the full join, and it's efficient. You can answer these queries in interactive time, right? But it has limitations also. First, it does not, it has two steps, as I said, right? And it first gets the most joinable, and then it ranks by correlation, right? But it does not consider the correlation score in the retrieval stage, right? And that's a result, you can end up with a low recall. And on the flip side, it doesn't consider joinability in the re-ranking stage. So let me show examples that illustrate this. Right. So suppose that we have a number of data sets. I say each line here corresponds to a data set, candidate data set that is returned, and with together with the joinability score and the correlation score. Right. And let's say we're returning the top 5 tables there. Right. In this case, because we selected the cutting point here at 0.9, sorry, right, we end up missing tables that are strongly correlated, but that have only slightly worse joinability, right? So you have, a lower recall. Another problem is that, when you're trying to retrieve these tables, and looking at these two examples here, one has perfect joinability and the correlation of 0.7, and the other one has 0.9 joinability, but perfect correlation, right? So which one is best? And the answer is, it depends on, your question. It depends on your application, right? So how can we address this? We did so by, generalizing this definition of joint correlation queries to weighted joint correlation queries. So now, instead of finding just the top K tables, we want to find those tables that maximize a weighting function that combines the level of joinability and the correlation. Right, and this is a way that we can actually take into account, user constraints and application requirements. And there are different choices for these weighting functions. In our paper, we actually use weighted geometric mean for that. And this is nice because it actually captures exactly what we proposed initially for correlation joins. When you have the weight for the join that equals 0, it's exactly what we had for the original correlation joins. And we can also see that when you have equal weights, you actually have W equals the square root of J times R, right? Right, yeah. All right, so how do we actually solve this, modified problem with the weighted join and correlation, right? So we propose a new hashing scheme, which we call QCR, that combines sketching with the fast top K query processing algorithms that are widely used in information retrieval for documents. So we propose this hashing scheme that derives terms that can be used in an inverted index, and that encodes information both about the keys and the values in a single term. Right, and by doing so, it reduces the problem of finding these correlated tables to the simpler problem of just finding set overlap. Right, and as I said, we can use widely known and efficient algorithms for top K query processing that have been proposed for document retrieval. So here we can, instead of having 2 steps, we can actually find these joint correlated queries in a single step. So the hashing scheme works, like as illustrated here. you start with your full table. You first do the same correlation sketch as I described before. And then we apply the QCR hashing to generate these terms, right? One term per entry in the correlation sketch. And these QCR index terms are defined by applying a hashing function over the hash over the key that was used in the correlation sketch. But now it appends a +1 or -1 to actually give an indication of which quadrant that value actually belongs to. And that's going to become clear in the next slide. Right. So the basis for the scheme is, this idea of quadrant count ratio correlation. And one of the reasons that we use it is it's simple and it has several properties in common with correlation, popular correlation measures. It yields values in the range -1 to 1. Right, it's close to 0 for uncorrelated data and +1 or -1 for correlated data. Right, so if you have, here your points, the RQCR can be computed by adding the number of points in the positive quadrants 1 and 3, subtracting the ones in the negative quadrants 2 and 4, and divide by the total number of points that you have. Right. And one thing to keep in mind is that in our case, in our scenario, we actually don't need to accurately estimate RQCR, right? And the next example is going to make this clear.
The figure in this example.
Sorry, I think I have an unwanted, sorry. Okay, sorry. Right. So suppose that you have a candidate table and a query table, and here the labels correspond to the keys, and the position of the point in the line correspond to the value associated with that key. Right. So the way that the scheme works is that first you do sorry. I thought that I had removed this. See if I have that in the next one. Yeah. Okay. My apologies. Okay. Right. So once you have this data, first you mean center the points, right? So you compute the mean of the values and you mean center them. And then you can classify the points. You have points that are not, that do not join between the query table and the candidate table. And here the examples are J and H. There are no corresponding points in the other table. You have the green points, which are points that correspond to keys that join. And not only that, they belong to the same quadrant. So you have B, C, and A, both they are above the mean here, and F, E, and D, they're below the mean here. And then you have the blue points here, which are points that join, but they are in the negative quadrants, 2 and 4. Right. So here, as I said, you don't need to compute the RQCR. All that you need to do to find positive correlations and find tables that maximize the ratio of the green points, and to find negative correlations, you need to maximize the ratio of the blue points. Right. So we did compare the hashing scheme against correlation sketches, and the results show that it attains higher precision and recall, and it has also a better balance between the ranking accuracy and joinability. One surprising result is that it also has a better space accuracy trade-off, in the sense that for the same level of recall and accuracy, QCR actually can do that with sketch sizes that are much smaller than what is required by correlation sketches. right? And if you want to see more details about these experiments and as well as the theoretical analysis, they are in our ICD 2022 paper.
Because I think I got confused. Can you go back one slide?
Mm-hmm.
Sorry, I think I got confused for the kind of the quadrants and the joinability. So in this example, right, kind of you have the two tables C and Q, and then kind of the position on the axis represents the actual value of the correlated table, the sort of correlated columns that you care about, right? Is that right?
So the position corresponds to the value associated with the key.
Good.
So here, so B would be associated with value 2, J with 1, maybe A would be 5, and so on, right? So the position on the line is the actual numerical value that is associated with that particular key in the table.
Okay, and then the letter like JBC.
These are the keys, right? The ones that we hash and that we use for joinability.
I see, which is why, so this is why kind of, I see, so like a B has to join with the B, but then correlated column. So like, so in that first table, like, let's say, I don't know, let's say the correlated columns are, I don't know, zip codes. So then I had maybe a lot of West Coast zip codes in the first table, and then a whole bunch of middle of the country zip codes for both columns, and then a whole bunch of East Coast maybe for the other column would be one way to look at this example.
So, so zip code, so is zip code your key?
No, that's the correlated, that's what I'm, so, okay.
So our correlations, we actually are, the correlations are computed for numerical values.
Yeah, you're right, so I needed different examples.
Right, yeah.
These are temperatures, maybe high temperatures, mid-range.
Right. So these would be like high temperatures and low temperatures, for example, could be.
Okay, okay, thanks.
Okay.
And other questions? This is going to be tricky, so it's
right. So the intuition here is kind of like as simple as essentially that now the hashing it encodes. Before we had like the hash and the value, and we'd have to perform the join, right? Here, what we're doing is we're encoding in the hash also the information about the value. That's it, right? So that allows us to do, this extra pruning.
yeah, that makes sense. Thank you.
Okay. All right. Okay, so that's the correlation joins are useful to find correlated tables, but there are the other kinds of needs when you're doing analytics, and one of them is when you find interesting, unexplainable features when you're analyzing data. And here's an example that's probably in many of my talks, which is a plot summarizing taxi trips in New York City, daily trips, and here showing 2011 and 2012. And you can see that it's pretty regular, the same days, about the same number of taxi trips, except that you have these weird dips here, these outliers. And as a data scientist, you may ask, are these data quality issues in your data? Was there a problem in data collection? Or can these be explained? Do these correspond to real events? And since I lived in New York, I moved here in 2011, I actually know what happened. So if you plot this against wind speed, you can actually see that the days with an unusually low number of taxi trips correspond to days with unusually high wind speeds, right? Because these were the 2 days where we had hurricanes in 2011 and 2012, right? And when I looked at this example, I kind of thought, is it actually possible that we can discover data to explain data, right? And this is a different, type of data discovery query where we are trying to come up with explanations for salient features in a particular data set, right? So given a data set and a data set collection, we want to find data sets in that collections that are related or can explain the salient features, right? And here we are looking at urban data as our motivation, and these data sets have information about space and time. They come like in NYC Open Data, you have thousands of data sets. They come in different spatial and temporal resolutions. And one of the challenges is how do you actually align these data sets that come in different resolutions? We'd like to find relationships, but you get these disparate data sets. Their attributes are actually incomparable. So how do you know what is a lot of rain and in terms of number of taxi trips, what is a high value for that? And that's not really comparable to, the high values for rain. And another challenge is, scalability. You have lots of data sets, thousands of data sets, and some of them can be very large. So the question is, how do you derive these relationships? How do you discover these relationships? And our approach to this problem is what we call data polygamy, because we're trying to find these polygamous relationships across different data sets. And to do so, we actually resorted to techniques that we borrowed from computational topology. So as a first step, we use a topological representation for this, the data sets. Each attribute in the data set is represented as a set of time-varying scalar functions that map point in space and time to a real value. And to deal with the different levels, different granularities, we actually use different levels of aggregations. That's why we have multiple scalar functions per attribute. But one benefit of using this kind of, let's say, encoding or modeling for the data is that now we have all the data sets represented uniformly. Each data set, will look like, will be a scalar function. Right. Another benefit here is the fact that these scalar functions naturally capture salient features in data sets, right? And salient features are going to correspond to spatial temporal regions whose behavior differs from its neighborhood, right? So you have these, critical points in the functions, these peaks and valleys that correspond to these atypical behavior, right? So once you have these features, in order to derive the relationships, what you can do is align the function space and time. So you can think of this as doing a spatial temporal join, right? And you attempt to, two data sets or two attributes are going to be related, right, if their salient features actually overlap in space and time. So you can have positive relationships when you have peaks that overlap, or you can have negative relationships when a peak overlaps with a valley, right? So this is kind of like the analogous to positive and negative correlation, right? And as it turns out, you can actually end up with lots of relationships, and many of them are going to be completely junk, right? They're going to be useless and meaningless. So to deal with those, we developed a restricted Monte Carlo procedure that tested statistical significance for these relationships and takes into account both a spatial and temporal proximity. And by doing that, we can actually prune a number of the coincidental relationships. And once we have these, we create a queryable index that, where people can ask, what data sets relate to what data sets based on the salient features, right? And I won't have time to go into details, but we've shown that this approach is scalable. All the different steps that are required to derive these relationships are embarrassingly parallel. So you can simply put those in a big cluster, and very fast you can compute all the relationships amongst thousands of different data sets. Right? And the last, relationship that I wanted to talk about is when you're actually dealing with outliers, right? So as I mentioned in data polygamy, one of the problems that we had was, you can have too many meaningless relationships. And we've pruned the relationships that are not statistically significant. But there are cases of relationships that are not statistically significant, but they are actually significant. And the example that I used for the hurricanes is a good one, in the sense that there are only 2 hurricanes, but they are actually the right explanations for the drops in the taxi trips. So we investigated this problem of, how can we actually come up with good measures that can enable us to explain outliers in data sets, right? So we have this notion of, we propose this notion of an outlier relationship is meaningful if it can predict it from nearby non-outliers. So the idea is like, if you can see that outlier coming, it's likely to be meaningful, right? And again, I won't have time to get into details, but the idea is, can we find some way of actually deriving meaningful explanations for these outliers. All right, so just to, kind of like try to put these different things together, right? So one of the big promises that I said in terms of data discovery is, if you can actually ask these data discovery queries. And I described to you 3 such queries, joint correlation, data polygamy, and predictable outliers. And there is a pattern that you can observe in these different queries, in the sense that they have 2 components. One is the alignment, is how you specify how to put together the different data sets. And the other one is the actual relationship that you're looking for. For joint correlation, it's join over categorical attributes, and relationship is that the joint tables have correlated attributes. Right. For data polygamy, you do a spatial temporal alignment, and the relationship is whether salient features are actually overlapping. And for pods, the idea is that you have approximate temporal alignment, and the relationship is over predictable outliers. So, to conclude, I think that there is a huge untapped value in open data, and as well as in enterprise data. We have lots of data, but it's hard to find relevant data relevant to a particular information need or analytical task. I hope I made a good case that we actually have to rethink how we can actually design systems that enable people to effectively discover data. We started to do this here at NYU with Auctus, but I think that there's a lot more work to be done in terms of the findability part of the FAIR principles for data. I talked about some data relationship queries that we have worked on that can be useful to explain data, to test hypotheses, as well as to improve machine learning models. And there are a number of other problems that we're looking at right now. I showed the shape of these relationship queries, alignment and relationships. So we've been looking at approaches to efficiently support a rich set of alignments, different kinds of alignments and relationship combinations, and how to do this efficiently, and actually support additional discovery needs. A big problem that I've been thinking a lot now about is how do we actually rank the results? What makes a data set better than another? And the answer is it depends, and we're trying to figure out how to address this in a more principled way. And last but not least, we're also very interested in visual interfaces, as well as interaction mechanisms that allow users to effectively explore and discover data sets. And here are my partners in crime for this project. And with this, I thank you, and I'd be happy to answer any questions that you might have.
Thank you so much. So now we're going to pause recording.